All right, so what I'm doing is to finish up the program that we were working on the other day. So it just so that I have closure, okay? This is mostly, I do this mostly for me, okay? Because I need to have the closure of knowing the program is done. All right, so let's move on. All right, so the main program is partially done, okay, up to this hold instruction, which is corresponding to the C code down to here, okay? So now we really have to implement the function called append. So we'll go ahead and do that. So before we do anything else, we can keep the halt instruction because I think I might want to halt after the call to append. So this is going to be where append will go. And on this side, we're going to move back to the append code, which is probably some of the more kind of tricky part of this entire program because this one has got parameters, it's got a local variable, it has got a lot of dereferencing, address off, and stuff like that. So the key here is to really do it step by step. And also, the first thing we need to do is to make sure that we understand what the C code is about. So we'll start with um, the offsets to various items. So the local variable pptr, or pointer to a pointer, is defined to be 0 because it is the only local variable, which makes it also the first local variable, which is at the bottom of the call frame. And then we calculate the number of bytes we need for local variables, which is the only local variable of the offset to the only local variable plus the size of that local variable, which is only 1 byte because it is a pointer. Now, the fact that it is a pointer to a pointer does not matter, okay? As long as it is a pointer, it takes up only 1 byte. All right, so now we go to the parameters. So head is the first parameter. So it is append underscore LVS1 plus because we have to skip 1 byte because of the return address. And then now we have new node. So there you go, which is the previous parameter, which is head plus the size of the previous parameter. Head is also just a pointer, so we just add 1 to that offset. So now we know how much stack space to allocate because of LVS, and so we'll go ahead and do the allocation and the allocation. So we have a LDIB and LVS, and then we subtract B from D, and then just kind of do the same thing except we add it back. And then now we are ready to return, which is a LDBD, and a increment D, and a JMPB. Okay, so that's how we return. All right, so in between, we have all the local variable storage allocated here. So now we can actually go ahead and try to implement line 36 and kind of move ourselves forward with this. So the other thing about this is when we are allocating a space, we can potentially push values on the stack. In other words, we're kind of combining the allocation and the initialization of local variables at the same time. It can be done, but it does make the code what quote unquote brittle, which means if I change the ordering of the local variables, it's gonna affect the assembly code, by a great deal. So I tend not to do that, but it is not incorrect to do that. It's just the resulting code is more brittle, in the sense that any changes to the C code can uh, basically trigger a massive amount of changes in the assembly language code. All right, so kind of keep that in mind. All right, so line 36 really just want to copy the value of head to PPTR. So that's a relatively simple operation. So all we need to do is to get the value of P head. So we get the address and then we do LD A. So now we should have the value of head in register A. Okay, and do about the same thing with PPTR or pointer to a pointer. And then we do a store, and that should accomplish line 36. And now we have a loop. So every time we have a loop, my way of doing this is to start with a label that marks the beginning of the loop and a label that marks the end of the loop. And then we have an unconditional branch, right before the end label of the loop to go back to the beginning of the loop because this makes it an infinite loop. So now with all of this, now we can go back and say, okay, but how do we get out of the loop? So in this case, we get out of the loop if what PPTR is pointing to is a 0. Okay, so how PPTR gets the value updated here looks kind of complicated, but that's not an issue when what we want to implement is line 37. So, that's how you might need to look at the program when you're trying to implement the homework assignment is really to focus on one thing at a time and not really get distracted by what seems to be the complexity of the rest of the code. All right, so what we'll do is we are gonna retrieve PPTR here. Okay, so we retrieve it into whatever register. Okay, because at this point it doesn't really matter which register I choose. So AD, LD, AA. Okay. So now register A is the value of PPTR, but we need to look at what it is pointing to. So we're gonna put it into register B, for instance, because I might need register A back. Okay, so that's why I'm loading this into register B because later on we can see that we are actually changing PPTR. So that means yeah, I don't think we have enough registers to to do this. Let me see. Let me think. Okay, I think we need to preserve A, and then here we can use register B and register B. There we go. So we can use register B to store whatever PPTR points to, and then we keep register A to be the address of PPTR. So when you are watching this, okay, you might want to pause the video and comment the program, and also make sure that you kind of understand what I'm talking about. Because you might want to draw a picture of the frame, and then just identify what is in each register, or also you can also go through the trays, and go through these specific lines. Look at how the registers, have the values change, and look at what is on the stack or what is on the call frame, and then you can actually have an understanding of how each line of these code is corresponding to what I just said. So that is important. Okay, I kind of intentionally did not, put in the comments into this program just so that you can uh, put in your own comments after watching the video and or after you figure it out by yourself. All right, so register B has whatever PPTR points to. Register A has the address of PPTR. In other words, no register actually has the value of PPTR because that really is not important to us. So that's kind of the deal. Okay, so now we can check whether PPTR what it points to is null or not. So let's do that. Um, so we're gonna do an and BB, and then if it is 0, it's time to get out of the loop. So this is rather handy. We don't have to kind of mess around with any additional logic here. So I'm going to use some additional indentation because now we're moving on to line 38. It is nested inside the condition, the while loop. So I'm just putting some extra indentations to help myself understand which part is the actual body of the loop here. All right, so now we're moving on to the most hairy part of this entire thing, which is, what is the address of the member next of the structure that is pointed to by a pointer that in return is pointed to by PPTR. Okay, so that seems pretty kind of long-winded and complicated. But if you wrote down what I just said, you just work on it one step at a time, kind of backwards. Because what I said was it is the address of the next member of the structure that is pointed to by a pointer that in return is pointed to by PPTR. So what we need to get to first is whatever PPTR is pointing to, because whatever PTR is pointing to is a pointer, which means that is the address of the structure, which conveniently is in register B already. So that means what is left for us to do is really just to calculate the address of the next member. So now we just load C with I think X underscore next, which is the offset from the beginning of the structure to the member called next, and then we just add C and B together. Uh, mm, I'm I'm just thinking whether I need to I can destroy register B or not. The fact is, the way I do things right here, I can in fact destroy register B because the register B is going to be reloaded when we get back to the beginning of the loop. Yeah, so we'll just put it into register C because register C is truly disposable at this point. All right, but the most important part here is we're done. As complicated as the right hand side may look like, we are done. Part of the simplicity is because we are taking the address of something. Because if you want to get to the value of something, you have to get to the address first. But that means getting to the address of something is the easier part. Getting to the value takes one more step. So that's one reason why this code looks deceptively simple. And then the other one is because I kept register B to be whatever PPTR is pointing to because I intentionally kept it here. Um, well, actually, I don't even have to intentionally keep it there because I need to compare that to 0. So that means whatever I need to compare to check whether it's time to exit the loop already has PPTR or whatever PPTR is pointing to stored in a register because that's the only way I can check it. Whether I use AND or CMP does not even matter because that's what I need to do. So right here, I can just say, oh, okay, since whatever PPTR is pointing to is already in register B, we'll just make use of it. All right, so what is left is to compute the right-hand side, excuse me, the left-hand side, but we don't have to do anything either because register A still has the address of PPDR. So that's all we need. Okay, we just have to do this and we're done. So this code is deceptively simple because line 83 to 85 is implementing line 38 in the C code. And you can also see how the C code looks kind of complicated with all the address of the pointer to the reference and so on. And also, there's an implicit dereference when we look at the pointing um, operator here. The assembly code is deceptively simple. So is that working or not? I don't know yet. Okay, yeah, because we have to check it. But according to my reasoning right now, it should work. All right, cool. So when we get out of the loop, we have to store new node to what PPTR is pointing to. Um, that requires some reloading of registers, because we did not keep track of all that stuff when we go through the loop. Because when we go through the loop, when we exit from the loop, register B is whatever point PPTR is pointing to, is the value that PPTR is pointing to, but we are not interested in whatever PPTR is pointing to on line 40, we need to know where it is pointing to. So that means that we have to go back and recalculate the address that PPTR is pointing to. So we'll start with the right-hand side of line 40, which is just figuring out the value of new node, which is a parameter. So that's how we do that. Append new node, put it into a particular register, it doesn't matter which one. Add AD, that's the address, LDAA, that's the actual value of new node. And then on the left-hand side, we have to get to PPTR first. And at this time, it is still in register A. So if I want to save myself some time, I can just do LDA. Okay. So because register A already has the address of PPTR, I don't want to have to mess it up. So I'm going to change everything here to use register B because register B truly is not useful anymore. So now so this is a change to the usual thing that I do, which is using register A for the right-hand side of a assignment, but it's okay. That's not a problem. Okay, so now um, register A is still the address of PPTR. So now if I load it once, register A becomes the value of PPTR, which is already the address of the pointer that I need to overwrite. So now we just need a STAB, I think. Yes. So now we just need a STAB because register B has the value of new node already, and register A is PPTR, and we are overwriting to whatever PPTR is pointing to. In other words, roughly speaking, when you see a dereference in the C code, it kind of equates to a pair of parentheses in the assembly code. Not exactly always the case, but close. All right, so that's done. And the last thing we need to do is to change whatever we have to change the member next of whatever structure that new node is pointing to and change that to a 0. So let me see what I can reuse here. Register B can be reused because register B is new node, so let's not mess around with register B. So we'll use register A and put a 0 into here. So this time register A is the right-hand side of line 41 in the C code. And the register B already has new node here. So we just need to calculate the address of the member next of the structure that new node is pointing to. So we'll put x underscore next into register C and then add register C to register B, or the other way around, doesn't matter which way. So I'll just do it like this. So register C is the address of the member next of the structure that new node is pointing to. And now we can just do a store. And that should complete the operation. All right, so this is what I think the code should work and should do. And so now it's time to test it. So that means I'm gonna put some code right before the halt instruction in the assembly code so that I can implement line 51 of the C code. All right, so line 51 of the C code is to push new node and also the address of head on the stack, and then we call append. Okay, so let's give it a try. So we go to here, this is main, and new node, put it into a register, doesn't really matter which one. Then we go add AD, LD, A. So now we have the value of new node in register A. And sometimes if you have enough registers to play with, you can pre-compute all the arguments into the register so that you don't have to worry about, oh, we just put something on the stack and we have to account for that 1 byte that we use on the stack. So, depending, this is sometimes I do this and sometimes I don't. Okay, so you kind of have to understand in both cases. Obviously, this is register B. So now we have register A containing the value of new node, register B containing the address of head, which is a local. They're both local variables of main. And now it's time to push them. So I can separate the calculation of the arguments from the actual code to push them on the stack. And if I do this, I don't have to worry about, oh, we need to add one to the offset, because um, when I calculated the address of head on lines 138 to 139, there were no decrement yet, right? So that means the stack pointer is still pointing to the base of the frame, which means I don't need the 1 plus at the end of line 138. All right, cool. So now we just do some pushing and then we will do the JMPI. So there we go. So we just have to do a decrement D, ST. So we have to remember the order of pushing. The last argument is push first, which is register A in this case. And then we decrement D and push register B because that is actually representing the first argument. All right, and then we have to remember to do the return address. So MDIA.6 plus decrement D STPA. So now we have all three items pushed on the stack. Time to jump to the function, which is append. When it comes back, I need to increment the stack pointer twice because both arguments are still using stack space and they are really not needed on the stack anymore. All right, so now would be a good time to do the halt instruction. Make sure I save the file. And then we need to run this in the C code. Oh, the C code is already here. That's excellent. The breakpoint is on the append. So I am going to, let me see, single step steps into, there's a way to step over, but I cannot remember the name of that command. Hmm. I just cannot remember. That's okay. I will set up a breakpoint. It'll be 53. Okay, so that sets a new breakpoint on line 53. So then I can continue the execution from what we had yesterday. It is on breakpoint 2. Um, that, okay, I'm a little bit confused here. So it says it is on line 52 of the C code. We are about to call node alloc. Okay, all right. So that means append is already called. Um, cool. So if append is already called, we should be able to see that the head local variable be not null anymore. Oh, it is inside node allocation right now. Okay, so that is interesting. It did not actually stop on the line that I wanted it to stop on. All right, we can still use this, okay? So what we need to do is do a backtrace, and then we say frame one. So what this is going to do is to use the #0 #1 to identify which frame we want to go back to in terms of examining local variables. So this would put the debugger back into frame one. It is not actually doing anything to change the path of execution. It is simply changing to which frame is the current frame that we are referencing. In other words, node we are actually the execution is actually in node allocation. However, we can now switch the context back to the frame of main so that we can check out the local variable values of main. So that's basically what this is doing. All right, so in main, we want to check out what is the value of head because head is affected by the call to append. So that means we can now say print head. It is not null, okay? So that's good because the head was initialized to a null. And we also want to print whatever head is pointing to, which should be a struct x that has a value of 15 because that's the only node we have created at this point. And then the next value should be null. So let's check that. Yep, okay, so everything checks out. So that means this is how append is supposed to work. It changes head to point to the first element of the array of pool, which is the first available node, and it also makes sure that the value of that node is 15 in this case, because well, that's actually how we put it, but that's also how we can identify whether it's pointing to the correct thing or not. Um, all right, so I think that's kind of what we need to do is to check that in the assembly code. So now we go back to River Spider and then run the assembly code again. Go. So while the program is doing this, I'm just going to re-emphasize the importance of really checking the program, like really step by step, comparing the C code behavior to the assembly code behavior, because that's because otherwise, if you're trying to write too much code before checking again, um, it just gets unnecessarily difficult to debug the program. All right, so at this point, we need to know whether the program is working or not, which means we have to know whether head is pointing to the first element of pool. All right, so let me go back to the source code because I think I have some documentation at the very end or not. Um, how did I do that? Oh, right, I did it on my tablet. And I don't have my tablet turned on. So, okay, that's fine. We can still do this. Okay, we can go back to the assembler, and then we go to the assemble tab because the assemble tab has all the information that we kind of need. Well, most of it, not all. We can see where the pool is beginning. So pool is beginning at location 0A. So we need um, head, which is a local variable to have a value of 0A. So now we just have to calculate, where is head, as a local variable of main. So now we do it the kind of typical fashion here, which is, indicating the location. Okay, since they're all in hexadecimal, might as well just kind of do this. So location FF is going to be 09, which is the return. This is the return address back to the entry code. There we go. And then the next byte down, would be that would be the local variables of main. And because new node is the second one, it is the one with a higher address according to how the labels are defined. So this one is new node, and so the next one down, which is FD, is going to be head. So according to the C code, head should now point to the first element of pool, which means it should have a value of, I think, 0.8. Let me double check. Um, Pool, it has an address of 0.8. Okay, that is correct. So we are now expecting the program, the last thing that the program does is to update location FD with a value of 0A. Okay, so that's what we're looking for. If we don't see that, then that means we have a problem. If we see that, it doesn't mean the code has to be 100% correct, but it is a very good indication. So we just keep going. Right here. Okay. So we do see the update of FD getting a value of 0A, so that's good. This one is fine because we are putting the null value, which is where head is, into location 0B, which is member next of um, the first struct X in pool, which is also um, what new node is pointing to, because okay, let me show you the C code that does this. So we are looking at this line of C code here, line 41, is what is causing this memory write to happen. All right, so everything seems to check out. Cool. All right, so that means I can now finish up the program, which is really just a repetition of what we have done already, except, this time instead of putting 15 into member V of whatever node new node is pointing to, of the structure that new node is pointing to, we are now overwriting with a 10, but the rest of the code is identical. So that means I can just copy and paste. So there we go. We just have to find out where we copy from. We are copying from line 119 to 150. So 119, 150, yank. This is how I do copy. And then P, lowercase p is paste. So there we go. And then we just change the 15 to a 10. And the rest should be identical. There are no additional changes here. So because I'm fairly sure this program is working, I'm just going to end the entire program here with the LDI A0, which is corresponding to line 55. Even though the return value is not really used by the entry code for anything, it's still okay to do it this way. Okay. All right. Um, cool. So now what we can do is to just run this code. Okay. You'll save this code, run it, and then we'll also run it in the C code too. And then we'll try to figure out what is going to happen. I think I showed you guys how what the C code is supposed to do anyway. So let me just do a continue on the C code. Okay, let me do a list here. Put a breakpoint on line 55. Okay, so Oh, okay. So we already have a breakpoint on line 50, on line 55. So we can now delete, the last one. D stands for delete, and 5 identifies the breakpoint. So this is how we can delete breakpoints in the command line interface. So we just continue execution, continue execution. Now we stop on line 55. And what we want to do is to print your head. It is still pointing to the first element of pool. We want to print the next member of the structure that head is pointing to. It is now pointing to the second element of pool. And we haven't, so it should be one is 15 and one is 10. So the easiest way to see what the elements are in the array pool is just to print pool. We can see how the value of the first item it has a value of 15, the value of the second item is 10, and the first one has a pointer. The next pointer is pointing to the second one. The second one and the third one, they both have no pointers because head is pointing to the first one. The first one is pointing to the second one, and that's the entire linked list. Um, the free pointer, on the other hand, should point to the third one, so we can also double check that, right? Because we want to double check to make sure that everything is working. So that this is in fact the third item in pool, and we can double check to make sure that is the case. So we look at the address of the third item, which is with an index 2, because we count from 0, and that is exactly the same. All right, so that is the behavior of the C code. We should see the same kind of behavior in the assembly code. So let's go ahead and run the assembly code, and then we double check whether it is happening in the assembly code or not. All right. So I'm fairly confident the assembly code is working because I debugged the program really step by step, in a very kind of bottom up fashion. So that means, every step along the way, I am double checking things before I proceed, which means, I could have still missed something. It's possible, but the chances are fairly low. All right. So now let's double check, what should happen, because without knowing what should happen, we cannot compare. We cannot tell whether the program is working or not. All right. So what we are expecting to see is 0C is going to be written to location 0B because that's how append works. Okay. So it's probably a good idea to write all this down. So let me pull up my little um, how do you call this? Stickies. That's right. Okay, so I'm gonna pull a sticky. This is my little sticky here because I need to write down what is supposed to happen. So I need to say that location 0B is going to get overwritten. Okay, so I'm gonna use exactly the same notation that we should expect in column C of the analysis tab. So 0B, okay, 0B should get a value of 0C. So even though it starts with that, because it's already the value at location 0B is currently overwritten with a 00 already, based on the program up to this point. So, that's going to be changed back to a 0C. However, location 0D should be 00. We are expecting the free pointer to point to location 0E, which is the third element of the array pool. So that means 10, location 10 in hexadecimal should update to 0E. And then head is, okay, let me see where head is supposed to be at. I documented that in the assembly code. There we go. So head is 0A. Head is not going to change. New node should change to the new node that is allocated. So that means, okay, where's my post-it? There we go. All right. So that means new node, which is at location FE, should point to the second item in the array, which is right here. That is location 0C. Okay. And I can double check all of these in the C code also, right? So because I can now go back to the C code and say, okay, what is new node in main? And new node in main is pointing to the second item in the array because pool plus 16 is the second item. And if you want to double check it, that's pretty easy because you can just go like, okay, tell me what is the address of the second item in pool, and that is the same here. Okay, so that means in the assembly code, okay, where's my post-it? Right here. So that means in assembly, because location FE is new node, it should be overwritten by the address of the second item in the array, which is starting at location 0C. Whew. Okay, so that's what we are expecting the program to do, and now it's time to double check it. And I want my post-it to always be on top, so this way I don't lose this when I'm scrolling in the analysis tab. There we go. So the updates are not going to be in this order. The first thing that we should see is the overwriting of new node because we are grabbing new node first and then we use it to call append later on. So that would be the first thing to update. And then in append, um, we are going to see, we first track down the end of the current linked list and then we change the next of the last structure of the linked list to point to the new thing. So that means 0b being updated to 0c is in fact, that is the correct order. And then we change the node that we are adding so that its own next member becomes null. So this is in fact the next thing that we should see. And then this is Oh, okay. So this should happen before this time because this is basically 10 is the location of the free pointer, and the free pointer should be modified before the call to append. So that has to happen either before or after FE got changed. Um, it would be before. Okay, there we go. Because when we call um, node allocation, this is what's going to happen. When that function returns with a value of 0c, that's when this is going to happen. Because fe is new node, and then we use new node to call um, append, and after the loop, this is the update to the member next of what pptr what to the next of the next member of the structure that is pointed to by a pointer that in return is pointed to by pptr. That's when this happens. And then lastly, this happens because we are also modifying the next of that member uh, to a null. Okay, so let's double check. Okay, look at the C code, make sure that I'm not remembering the code incorrectly. Yep, okay, so this is how 0b, location 0b gets 0c, and this is how location 0d is getting a 0. So that is the correct sequence here. All right, so you can see how I am predicting what the program is supposed to do before I even take a look at the analysis tab. And this is really important because that's how we debug the code, because you have to know what it is supposed to do in terms of memory read and write, well, particularly write operations, and then you are cross-checking to see if it is happening the way that we thought it should happen. So if there's a difference between the two, that means either I missed something or I did something incorrectly. In either case, it should be investigated. Okay, so now we're gonna check all of this stuff here. We're expecting location 10 to update to 0e. And it happens right here. Okay, excellent. And the next one is FE gets the value of 0C. There'll be some additional stuff happening on the stack, because we push arguments and then we push the return address, blah, blah, blah. So there are some additional memory writes, in between, which is fine. And there we go. Okay, so this is, uh, this is the update of the new node local variable in main. And then the next one is 0B gets 0C, and there'll be, after a while, some updates here. Okay, so this one I did not expect. Huh. Hmm. 0C gets a value of 0A, and that's before we call append. Okay, so this one is a little suspicious. Okay, so I'm gonna make a note here. And this is also something that you should probably do, is to kind of make a note of, things that we don't quite know why it is happening. So row 246, we have a write to location 0C, and the value that we overwrite it with is 0A. Um, 0C is the... Oh, right, right. Okay, now I know why this is happening, because I forgot. I forgot that main is changing member V of what new node is pointing to. Okay, there we go. And this is what new node is pointing to, which is here. And because V is the first member, and that's why this is the update. This is let me show you. This is corresponding to this line over here, line 53. I forgot about that. Okay, so accounted for, okay, which is important. Okay, we accounted for that particular memory write. So now we are expecting, the program to do the rest, which means we're expecting 0B to update to 0C. Okay, there we go. So we move on and on and on. Do, 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 do. All right, okay. There we go. Okay, cool. So you can see how this cell here matches exactly what we are expecting. And then lastly, we're expecting 0D to update to 00. And that's right here. And so the program seems to be working entirely. So now, I just have to scroll all the way to the end of the code here and make sure that the stack pointer is balanced, okay? And we do end up at the only one halt instruction that is left in the entire program, which is the one at location 09 on line 7. So that concludes the implementation of the entire program. All right, so it's already done. Okay, so I'm going to pack up, this particular program, put it into a little zip file so that you guys can have access to it. And once again, the most important part here is not, okay, I emphasize, is not to memorize, any of this code sequence. Okay, you need to know what they do. Okay, the code sequence here is just how I do it this time. There may be other ways to get it done. So the how it is done is important, but not nearly as important as what is being done. Okay. And the why is simply because that's how the C code, what the C code is specifying. So that's also important. For the homework assignment, it is important to kind of use the technique that I'm showing here, which is kind of write some code, check out what the code is doing, and then don't move on until you have debugged the code. And the debugging process means you have to know what kind of memory write operation is expected, and if that is not happening, then you have to go back and debug the program. To debug the program, you can use the trace analysis, which we just call the analysis tab in the spreadsheet. So let me go back to the spreadsheet here. And then all you have to do is to follow your own code, line by line, instruction by instruction. I mean, there's no easy way around this. I mean, this is how we debug programs that are written in assembly code. And of course, with commenting, your code is going to be a whole lot easier to debug because the comment would actually show up in column G, which means, along the way, as you read the effects, the side effects of your code, you'll be also reading your own comment of, what that line of code is supposed to do. And if it is not doing what it is supposed to do, then you stop right there and then you go backwards and figure out, okay, why does this value is not in, why is this register not put into the correct location or not getting the correct value, because you know what it is supposed to be getting and it's not getting that value. So you can now execute a program, quote unquote, backwards until you find out why or how it got the wrong value to begin with. And that's, so the trace here, the analysis tab, is actually a very essential component to help you debug your program. Um, it doesn't make it, I mean, okay, it does make it a little bit easier, but it really doesn't make it super duper easy like writing code in C++ plus plus in VS Code. It's just not, okay? That is not the nature of writing and debugging code in assembly language. Um, all right, so I think I have repeated myself a lot of times already, and you guys are already getting tired of that. So I'm gonna stop the recording right now. You push it onto YouTube and then share this file with you. All right. Well, have a nice weekend, and I hope your experience with dealing writing the homework assignment is mm, it's going to be challenging, but at the same time, I hope you learn a lot from that experience, not only in terms of technically understanding, how the stack is used, what is a frame, how to access local variables, how to deal with pointers, how to deal with a member of a structure that is pointed to by a pointer, blah blah blah, and etc. But also, having a chance to exercise your problem solving skills, because I I know almost for sure that you're gonna need to exercise your problem solving skills, because this kind of program is not easy to write. Okay, that's just the nature of it. All right, I'm gonna stop here.